Okay, let's see the contents of this video first. First, I will explain what is discrete cosine transform, and then I will highlight its applications, advantages and disadvantages. Then I will explain how to compute the two-dimensional forward DCT and inverse DCT, and how we can compute the DCT basis functions. After that, I will explain one MATLAB code that will generate the two-dimensional DCT basis functions. And then I will explain the two methods which will be used to compute the DCT. The one is which is utilizing the FFT, and second one which is utilizing the transformation matrix. After that, I will explain how the image compression is achieved using discrete cosine transform. Then I will explain the MATLAB code that will be used to compress an image using the MATLAB's DCT2 function, followed by the MATLAB code for image compression that will utilize the dctmtx MATLAB functions and block processing for achieving the image compression. So let's go ahead. Before going further, I request you to please watch following my these two videos. One is about the wavelet transform analysis of images using MATLAB and Simulink, and second one is also the same, but implementation is done using the Python. These two videos link actually you can find in the description. So now let us see what is discrete cosine transform. Actually, the discrete cosine transform DCT represents an image as a sum of sinusoids of varying magnitude and frequencies. DCT actually is an outcome of the efforts to make the DFT. DFT means the discrete Fourier transform having real values instead of complex values. So the DCT, you can say it is an equivalent of computing the two endpoints DFT of a signal which is made even symmetric by its extension. So the DCT coefficients, as when compared with the DFT, they are real valued. Therefore, the hardware implementation of the DCT is much easier than the implementing the DFT. So also, if one can utilize fast Fourier transform structures to compute the DCT, obviously it will be much faster computation. Therefore, it has become the choice for many applications. The DCT actually has the property that for a typical image, most of the visually significant information about the image is concentrated in just a few coefficients of the DCT. So this property is known as the energy compaction property. Therefore, DCT finds its application in image and video compression. So DCT is at the heart of an international standard lossy image compression algorithm which is known as JPEG, which is very popular to represent image compression. Besides this, DCT has actually the vast applications areas such as JPEG, as I already said. Apart from this, it is found in HEIF image compression, WebP, BPG, etc. Also, it is the main constituent of various video compression codecs such as H261, Motion JPEG, MPEG-1, MPEG-2, H263, and then currently widely utilized H264, which is known as Advanced Video Coding, or MPEG-4, and then H265, which is the latest one, that is the high efficiency video coding, and then WebM, etc., various video compression algorithms. And it is also very popular in audio compression. It finds its importance in AC3 format and modern AC4, and it is a part of a very popular MP3 audio compression algorithm, MP4, AAC, AAC Plus, and Windows Media Audio, etc. You can find the importance of the DCT in the speech coding such as voice over IP and in the digital radios. And also you can, of course, solve a partial differential equation using the DCT. Besides all these advantages, it has a few disadvantages also. For example, a common issue with the DCT compression in digital media are blocky compression artifacts caused by the DCT blocks. So the DCT algorithm can cause the block-based artifacts when the heavy compression is applied. So in this image, you can see it's your JPEG image. When the heavy compression is applied, and after zooming it, you can see that these are small square blocks in the face you can see. So this is known as the blocky compression artifacts. So these actually in JPEG, these are small 8 by 8 pixel blocks. Also, if you truncate the higher spectral coefficients in DCT, they result in the blurring of images, especially where the details are high. And if there is a quantization of the low spectral coefficients, they introduce the graininess in the smooth portion of the images. So these are few disadvantages of DCT in image and video compression. Now let us see how we can find the two-dimensional forward discrete cosine transform of an image fxy having size m by n. So that you can achieve using this equation 1. So this is your image fxy, and here it is multiplied with these two cos pi 2x plus 1 p upon 2m, cos pi 2y plus 1 q upon 2n. And these are two coefficients alpha p and alpha q. So after implementing this equation, your fxy is converted into a matrix fpq that is equivalent in the size of fxy, and it is carrying all the DCT coefficients. So this equation you can implement in software by writing 4 for loops. So, the 2 for loops actually for the p and q, where p is varying from 0 to m minus 1 and q is varying from 0 to n minus 1. So how to compute this equation? First, we substitute the values of p and q. For example, I substitute, let's say, p equal to 0, q equal to 0. Then I vary x and y both from 0 to m minus 1 and 0 to n minus 1. And after that, we change the p and q. For example, p equal to 0 and q equal to 1. And then again varying x and y. So similarly, by covering all p and q values in this range, you can compute this fpq matrix, which is carrying all the DCT coefficients. And these coefficients alpha p and alpha q are given by these equations. For p equal to 0 and q equal to 0, they are simply calculated by 1 upon square root m and 1 upon square root n. And other than p equal to 0 and q equal to 0 values, they are simply equivalent to square root 2 upon m and square root 2 upon n. Now let us see how we can compute the inverse transform, IDCT. So for an image fxy of size m by n, the inverse transform can be achieved by this equation. So this was your matrix, which is computed by the equation 1. I mean, it is carrying all the discrete cosine transform coefficients fpq. And now we are varying x and y. So here we are substituting x and y first. So substituting, let's say x equal to 0 and y equal to 0, then varying the loop for p and q. Similarly, we will write x equal to 0, y equal to 1, then varying these two loops again. So here you have to implement 4 for loops again. So the procedure is similar as we have applied for FDCT. Okay, and the equations for alpha p and alpha q remain same when you compared with that equation 1. So this part is same. So if you compare equation 1 and equation 2, you will see that this part is common between these two equations 1 and 2. So that is alpha p alpha q cos pi 2x plus 1 p upon 2m, and then cos pi 2y plus 1 q upon 2n. So this part actually is known as the basis functions of DCT. So here if I can vary p, q and x and y, all 4 variables, I can generate the basis functions for two-dimensional DCT. So for example, let's say my image size is 8 by 8. So suppose all the 4 loops are varying from 0 to 7, I mean 8 times, then I can generate this type of basis functions. Okay, so this is for p equal to 0, q equal to 0, okay, and this is p equal to 0, q equal to 1, and so on. So here you can see that the horizontal frequencies are increasing from left to right. So if you go from left to right, you can see that horizontal frequencies are increasing. And if you go from top to bottom, you can see that the vertical frequencies are increasing. So this first part is actually a constant matrix, which is known as the DC basis function, and it can be used to compute the first DCT coefficient, that is also known as the DC coefficient of DCT. While other coefficients are known as AC coefficients, because in the first coefficient we get a constant value. So constant value is representing actually the zero frequency, that's why it is known as the DC content of the image, while all other matrices are carrying the varying values, that's why they are known as AC coefficients of DCT. So actually, what is the need of calculating the basis function? Actually, for a particular size, let's say 8 by 8, we can compute these basis functions and we can store them into an array, and later they can be utilized to compute the DCT of a particular image segment of 8 by 8 size. Okay. So this is the MATLAB code to generate these basis functions. So here we are taking m equal to 8, n equal to 8 means I'm taking a small image segment of 8 by 8, and then just initializing this matrix, and as you can see you have four for loops. Okay. One where p is varying from 1 to m. Actually MATLAB index is starting from 1. So to compute sigma, let's say p equal to 0 to 7, I'm just subtracting 1. So small p equal to capital P minus 1. Just it is for adjusting the indices. So and similarly the q is varying from 1 to n. If you remember this equation where p is varying from 0 to m minus 1, and q is varying from 0 to n minus 1. Okay. And here with these conditions I am actually calculating the two coefficients alpha p and alpha q. If both p and q are 0, then alpha p and alpha q both are square root m and 1 upon square root m, if you remember from the previous equations. Otherwise they are simply square root 2 upon m or square root 2 upon n. Okay. And in the next part, these are two for loops for x and y. So there are total four for loops. So here we are computing that equation. So that means this is our alpha p into alpha q into cos pi p to x plus 1. Again, x is modified as x minus 1 because MATLAB index is starting from 1 instead of 0. Okay, and this is your cos pi q 2y plus 1 upon 2n. So that equation is written, and here the computation is done. But here actually I'm converting all those computed matrices as image. So later I will display all those images in combined format as I have shown you. So here you can see that computed image is first converted into unsigned integer 8 and then converted into the RGB with the color map of copper. You can use any of your color map, for example the pink, jet, etc. And I'm defining the file name by which I will save this image. So I'm saving the image with the name P and Q. Okay, so you will get the images like 00.png or 00.png when both P and Q are 0, and the next will be the 01.png and so on. And then I am writing all those images in 64 by 64. Actually the original image size is 8 by 8, so it is very small size to display. So I'm just enlarging them so that you can clearly visualize their structure. with the interpolation nearest. Okay, and then I'm displaying all those 64 images calculated in a montage by the montage command. So montage command actually is reading all the images which have written in the current directory. You can see exploring technology / video 27. So using image data store, I'm reading all the images, and all the images are now displayed in that 8 by 8 format. Okay, so let me run this program, and I can show you that how these basis functions are calculated. So let me go to the editor. So MATLAB editor is here, and this program is already written. So I'm just pressing this run button, and let me show you my current directory also. So this is my current directory. So no image you can see related to those basis functions. So after execution of that function, you must be able to see all those 64 images here. So I'm running this program. Okay, pressing this button, change folder, and this program is running. You can see MATLAB is busy. Okay, you can see this is the output which I am getting. So here all 64 images of size 8 by 8. You can see this is your first coefficient, which is constant, and then here you can see the horizontal frequency is increasing, here vertical frequency is increasing, like that. So these basis functions can be utilized to compute the DCT coefficients. Okay, and let me see my current directory, and yes, in the current directory you can see all these images. 64 images are saved. So first image is 0 0. I'm in the p equal to 0, q equal to 0, then p equal to 0, q equal to 1, 0 1, 0 2, 0 3, like this up to the 77.png. So all 64 images are here. You can change the actually the color map to represent these into the different color styles. Okay, so now let me come back to my presentation. Now let us see how we can compute the DCT of an image. Actually, we can compute with help of these basis functions also, but this is not a flexible approach, because once the DCT basis functions are computed, they are fixed for a particular image segment. I mean, if you compute this for 8 by 8, then you can apply the DCT only on the 8 by 8. Okay, so that is not a good approach. Actually, we have two different approaches. The one is the transformation matrix approach, and the second is the FFT based approach. So let us see first one, the transformation matrix approach. So this method is suitable for small image segments such as 8 by 8, 16 by 16, etc. For this, a DCT transformation matrix T is computed first for an M by M image segment by following equation. So this is the equation by which you can compute a transformation matrix for a M by M image segment. Okay, so here you can see that for p equal to 0 and q equal to 0, it is 1 upon square root m, or for q from 0 to m minus 1, it remains the same value. So that means the first row will have the same value, 1 upon square root m, for all columns. After that, it will change to this value depending on the value of p and q. Once this transformation matrix is computed, you can find the DCT coefficients of that image segment by this equation. So here you can see that this is your image segment. So this is your image matrix, then multiplied with this T matrix, then multiplies with this T transverse matrix. So if you do this simple operation, you get the DCT coefficients matrix. Okay, and similarly you can find the inverse also. Since T actually it's a real orthonormal matrix, so its inverse is equivalent to its transpose. So therefore inverse DCT can be found by this equation. So you can recover your image fx by this inverse operation. So this is FPQ is your DCT coefficient matrix, and then same matrix, transformation matrix, is put here, T and then T dash, that means the transpose. So by this operation you can get your image segment fxy back. So in MATLAB, DCT transformation matrix T can be computed by executing this function dctmtx. So if you execute this function dctmtx, you can generate any size transformation matrix. And the second approach is based on FFT. So this approach utilizes the FFT structure for speedy computation of DCT. So therefore, it is suitable for large input images, and in MATLAB, it is achieved by executing this DCT2 function. So if you go to find the DCT of small image segments, you must prefer the first approach. And if you want to find the DCT of a large image, then you can go to this approach, FFT based approach. Okay, I will show you both the approaches by writing MATLAB codes, how they can be used for the image compression. Now let us see the image compression using DCT, how we can achieve actually image compression. So as we know that DCT has very good energy compaction capability. So it means the information is being carried by fewer DCT coefficients. So therefore, large amount of coefficients can be neglected to achieve the image compression. So that is the fundamental behind the compression. So here you can see one example. This is my 8x8 image segment. So you can consider this is your 8x8 image, and if you take the DCT of it, you can see these DCT coefficients. So you can see this first one, which is known as your DC component, which is the largest one in the DCT coefficients. And just compare the other coefficients values. You can see they are very small in size. For example, 0.011, 3.7, minus 4, 4.73, 0.7, 7.2, 0.9. You can see very small coefficients, as compared to this first one. Even some larger coefficients are also there, like 11, 13, 12, 20, 25, 23, etc. So you can see that you can achieve the image compression by simply making these small coefficients to the zeros. That means this is known as the quantization process. So you can simply make them zero. This is how you can achieve the image compression, by making these small coefficients zero. So now let us go to the MATLAB code for image compression using the FFT based approach. Okay, as I have explained you that FFT based approach is achieved by executing this MATLAB function, that is the DCT2. So I'm utilizing this MATLAB function DCT2 here in this case. So when you execute the first few lines, you can see with the UI get file, you will get a system dialog box where you can choose your grayscale image, and then your image is read by this imRead, and your whole image information goes to img variable. Then with this function DCT2, you can see here I'm taking the discrete cosine transform of this image. So DCT2 of this image, all the DCT coefficients will go to this matrix C. So here I am actually showing you the DCT coefficient matrix with this command. I am show, just taking log to highlight the coefficients differences. If you don't take log, you will get a black or dark image. Otherwise you have to take log so that you can differentiate the magnitudes clearly. So taking the absolute values of C and then taking log, you can display these DCT coefficients properly. So with the title DCT coefficients before truncation, I have not used any truncation here. They are just original DCT coefficients. And for representation, I'm using the color map of jet with a color bar. Now I am doing the truncation process. So that is a coefficient truncation. Here you can see that all the coefficients of C which have the value less than 10, they are simply neglected, and that means they are made to 0. So this coefficient truncation is done with this equation. And then now you can display the truncated DCT coefficients in another image. So for that, I'm taking the another image and I am showing all those truncated coefficients. So you can have the comparison between the before truncation and after truncation. So you can compare those DCT coefficients. Then I'm taking the inverse discrete cosine transform with IDCT2 function. So this is my actually the recovered image, but it is in double data format. So I have to convert that into proper image format. So for that, I am just writing this image into the current directory in form of JPEG with the quality 100. So what I am doing, I am writing the original image IMG, and I am writing this reconstructed image CT with the same quality index 100. Okay, so both are in JPEG format. So you can compare the size of these two images. I mean the original image and then reconstructed image after the DCT coefficient truncation. So, and here I have shown both the images side by side. I mean your original image and the reconstructed image. So you can have the comparison of the quality. So let me run this program in the MATLAB. So let me jump to the MATLAB editor, and this program is written already. So here you can see that truncation is done with this equation. That means all the coefficients having values less than 10 will be made 0. So let me run this program, and it asked me to choose the file. So I'm taking this paper image, and here you can see the various coefficients. Yes, here you can see the two images side by side. So this one is your original image and this is your DCT compressed image. Okay, so quality wise there is no difference almost. And here you can compare the DCT coefficients before truncation and after truncation. So DCT coefficients before truncation, you can see that this matrix has the color towards the red and yellow. So from the color bar, you can see that these coefficients are at the higher side. So after truncation, this matrix becomes blue. It means the coefficient values actually are now approaching to the lower side. Okay, so because all coefficients above 10 are made to 0. So by this color information, you can see that there is a reduction in the amplitude of these coefficients. So let me see actually the sizes of those images. So for that, I have to go to my current directory and let me find those two files. I mean the original one and then compressed one. So here you can see that these two files, I mean the original file and then DCT compressed image. So just place the cursor. Its size is 169 KB. 169 KB. And now let me place the cursor on DCT compressed image. So here you can see that its size is 159 KB. So there is slight reduction in the size. The original is 169 and after compression it is 159. You can achieve more compression by neglecting the higher magnitude. So instead of 10, you just change it to 20. And let's see how much size reduction I can achieve. So simply run it and selecting the paper, open, and here I'm getting the original image and compressed image side by side. So again, there is not much change in the quality. And let me see the size comparison. So let me see what size I achieved. So just place the cursor and its size is obviously 169 because it is before compression, and its size is 145. So initially it was 159, now it is 145. So I'm getting the reduction of 20 and more in this case. So if you truncate more DCT coefficients, you will get more reduction, but at the same time the quality of the image will decrease. Okay, so now let me come to my presentation back, and I will show you another example. Now I will discuss the MATLAB code for image compression using the DCT transformation matrix. So this was another approach, as I discussed. Here, instead of using the DCT2 matrix, which is based on FFT approach, I'm using a transformation matrix approach, which is suitable for a small image segment. So with these lines of code, you can see with the UI get file, again you can select your image, and the imread is reading your image and putting all the information in img variable. Now with this equation t equal to dctmtx 8, I am getting the 8 by 8 transformation matrix. See, my image size is bigger. It is not 8 by 8. My image size is 512 by 512. But I am taking the dctmtx 8 by 8. Okay. So what I will do now, I will divide my whole image, the bigger image, into the small image segments of 8 by 8. So I will now do the processing on this 8 by 8 image segment. So that's why I'm using this block processing, which is a MATLAB's inbuilt facility to do this block-wise image compression. So I will take one block of image at a time, then I will find its DCT, and then I will neglect its coefficients. I mean, I will simply quantize its coefficients. Then I will take inverse DCT to get the image segment back. And then I will combine all these 8 by 8 segments to make my image as a whole image. So here you can see that with this command, I am just defining the DCT operation that will be applied on that image segment. So you can see that this transformation matrix T multiplied with the block struct dot data, it means that 8 by 8 block, and then multiplied with T transpose. If you remember the DCT operation, then it was the T matrix A then multiplied with T transpose. So that is defined here. Now with the MATLAB block processing function, I am computing the coefficients, DCT coefficients of all 8 by 8 blocks found in an image. So here you can see that your image is passed, then here you are defining the block size, and here you are defining the operation, this one, okay, this one here. So this block processing function, what it will do, it will take 8 by 8 blocks from image which you have passed, and then it will do the operation DCT, I mean this operation TAT inverse with each 8 by 8 block. So in this C, you will get all the DCT coefficients by this approach. Now we are doing the coefficient truncation. So I am applying the mask. It's a fixed mask, and here you can see this mask that all the coefficients are made 0 except these coefficients. So these few diagonal coefficients, I mean from top left corner, are considered because the first one you have to consider it in any way, because it is your DC content, which is the maximum coefficient of your DCT, and it is carrying all the basic information, and few high frequency components are selected. So this is how you can select your coefficients and how you can reject the remaining coefficients. So what I have to do, I have to simply multiply this mask to the coefficients. Okay. So again, I have to do the block processing. So here you can see in the truncating DCT coefficients. Here you can see with that block processing, you are passing this coefficients, DCT coefficients, then you are defining the 8 by 8 block, and then you are doing this operation. So in this operation, you can simply see that mask is simply multiplied element by element with that block of 8 by 8 DCT coefficients. So by multiplying this mask, obviously your top left corner few coefficients will be preserved, and then rest will be made 0. So now we have to take the inverse transform. So we are defining the inverse transform again. That is the T transpose, and then 8 by 8 block, and then T matrix, and then doing this operation on all blocks of your image. So here in INBC you get your image which is compressed actually by neglecting various high frequency coefficients from the DCT. And for comparison point of view, again we are writing these images to the current directory. So this is your original image and this is your compressed image with the same quality index of JPEG, that is 100. And here we are displaying these two images, original and the compressed image, side by side for comparison. So let me run this program in the MATLAB so we can have the better idea. So just opening this in editor, and this program is already written. So I'm just pressing this run button. Okay, so it is asking me to choose my image. I am choosing this Lena, and let's see what output I achieve. So you can see this these two images. So this one is your original image and this is your DCT compressed image. So quality wise there is not much difference. There is a slight blur actually in this image because and that is natural because we have neglected all the high frequency components. We have, although we have kept few at the top left corner, but we have neglected most of the high frequency components. So obviously the blurring will be achieved. So no surprise, but still this quality is acceptable. Okay, so now let me see the image size. So for that, let me go to the current directory, and here you can see these two images. So these two images, I mean this original one, and its size is 158 KB. And let me see the size of this DCT compressed image, and its size is only the 70 KB. So you can see that there is a huge compression. The original is 158, now reduced to only the 70 KB by this approach. So this is actually the more effective approach. And let me tell you, this approach is actually the basic building block of JPEG compression. So if you go through the JPEG compression algorithm, this is the main or this is the starting point. It means the image is first divided into 8 by 8 blocks, and then each block is taken, DCT is found, and then all the coefficients are thresholded, although the thresholding is slightly different as I suggested. And after thresholding they are encoded into bits. That approach is also slightly advanced. So if you go to the JPEG theory, you will find that this approach is a basic or starting approach of the JPEG. Okay, so that's it for this video. I hope you have enjoyed this and learned a lot of things about the discrete cosine transform. So I really thank you all for watching this video. I request you to please like it, share this video. So wait for the next video. Till then, goodbye.